Okay, so this is just the list of equations. So this is the gradient, this is the divergence of a vector, this is the cross product, and this is the Laplacian. Okay, so just yeah. Then the equation that you will be given is the first ones for the chapter 4. Those are the yeah, I will upload the video. Okay, I will upload the video. Okay, so yeah, but this formula sheet I can upload it already, so it will be given to you in the exam, so you don't have to memorize anything. So this is the Maxwell's equation for electrostatics. This is the Gauss law in the differential form, and this is the Gauss law that you have seen in physics 2 before. This is the Kirchhoff's law, the conservation of electric field in differential form and in integral form. Now, in order to simplify things for you, I would anything that is here will not be included in the exam. I will not give you this. So what is interesting for me here is this, because this is something that we did that is new, probably the energy density in a capacitor, right? And this is the relation of the electric field to the potential. And this is also something very important, the relationship between the conductivity and mobility. This is mobility and the volume charge density, and also the density, the current density, the relation between the current density and the conductivity of the material and the electric field. Okay, so this is something that I would give. Then we went for the boundary conditions of the in electrostatics. So the boundary conditions, this is very important here, because it will be a good part of the exam will be also on boundary conditions. So if you have any two media, let's say this is a media that has epsilon1 and a media that has an electric field epsilon2 and a permittivity epsilon E2 and permittivity epsilon2, then let's say this is the X and Y. So the electric field will have a normal, well, a tangential component, which is along the x-axis in this case, and the normal component along the y-axis that is normal to the surface. This is the surface. This is the interface. So at this surface, those ones apply. So the tangential are equal. The tangential are equal. And yeah, so this is a relationship between we know that D is equal to epsilon E. So we know this. So that okay, yeah. So that those are the two ones for tangential, and those are the two ones for the normal. So you can see that the normal, so the normal of the electric flux density at the surface, the difference is equal to the charge density, the surface charge density at the surface in the interface between the two media. Okay, so this is very important. As an example, if you have the first media is a dielectric and the second medium is the conductor, we know that inside the conductor the electric field is 0, and that's why the tangential is 0. And the norm, of course, the normal also is 0, but the normal of the dielectric is not 0. Of course, we apply this. This is 0, and then we got the normal component of the electric field inside the dielectric. So this is something that is very important in the exam. Then we went to chapter 5, and chapter 5 is mostly about the same thing as magnetostatic. This is something that we have seen. Again, as I mentioned, this one will not be given. I will not give you the electric field, the magnetic field for this kind of thing, just because we have seen this. My interest in this will be this one will be the Gauss law for magnetism, this one, which we already know. This is the integral, the form, the differential form. Okay, and which is equal to 0, and the one that we all see already, it's like a Gauss law for the integral over surface of any of the magnetic field is equal to 0. And now we know why this. For example, if you have any surface, if any closed surface, and you are trying to calculate the flux that is coming out of the magnetic field, in fact, the flux is always 0, just because in any, let's say, if you take any magnet, even if you cut the magnet, there is always a north and the south poles of the magnet, which their flux cancel each other. Okay, even if you break the magnet, as I mentioned in physics 2, so if you break the magnet will rearrange itself in a north and south pole. You will always have a north and south pole, and their flux will cancel each other. That's why the integral of the magnetic field, of the flux of the magnetic field, or the flux of the magnetic field out of the surface is always equal to 0. And this is also Ampere's law that we have seen in physics 2. Yes. So this we have seen, the Lorentz force, when you have the electric and magnetic field. So for me, this is the most important thing, this part and this part. Okay, I will give an example. Vector magnetic potential is a vector where it's equal to the cross product of nabla times the potential. For example, I can give you A and ask you to calculate the magnetic field. Okay, and then it could be the following. I give you A, let's say in cylindrical coordinates, and ask you to calculate B, the magnetic field. Then you have to go here and calculate and do this operation. Yeah, for example. Okay. This is like a Poisson's equation for magnetism, and this is the Laplacian of the vector potential vector magnetic potential is equal to minus mu, and then the current density. Okay. Any question? So this is what we will have covered during this the exam. Any question? So for chapter 5, this is chapter 5. This is chapter 5. This is chapter 5, and I can tell you that. Let me make it clear. What is in blue is the one that I will cover. I will delete everything, and I will tell you this is what you have to focus on. This one, okay, and this one, okay. Now so I added this one. I added this part because this part is easy. I can give you a vector magnetic potential and ask you to calculate B. Now let me also give you something that is very important. I mean to help you also. This is also very, very important. So chapter 3 and chapter 4 will be the core of the exam. Okay, right? Chapter 5, it will only be a bonus question. I think a bonus question will be on something like over 10 or 15, 10 points or 15 points. So basically chapter 5 is not included in the core of the exam. You will get, I think, 3 or 4 problems on chapter 3 and 4. Okay, that is strange. You can't hear me? Okay, so chapter 3 and 4 are the exams. Chapter 5, I will give a bonus question about it. Can you hear me?
Yes, sir.
So chapter 5 is a bonus question, and it will be probably 10 points. I still need to think about it, but this is what I mean, yeah, if you come ready with chapter 3 and 4 and you don't want to do the bonus question, you are fine. If you want to earn some points, you need to look at those those two ones, this and this. Okay, any question? No, no, as I mentioned, only this, yeah, only these ones. Okay. I don't know. I mean, the questions I don't know. Let go, because I have to go at 2:30. So I mean, frankly, the questions is not, and the number of questions is not really important. Whatever number of questions I will give you, it will be sufficient. The time will be sufficient. Let's start, because we did not do any examples for boundary conditions. Let's start by boundary conditions. Okay, boundary conditions, which is chapter 4. Okay, boundary conditions. Now, this is a type of question that you can have. Of course, you can have others. But you have medium number 1. This is medium number 1 that has permittivity E1, and medium number 2 permittivity E2. Okay, and this is the XY plane. The XY plane, for example, I can give, this is the XY plane. Okay, so you have two media, one E2 and one E1, and this is the surface. This is the surface, and this surface has a charge density rho s. And then this is the XY, and this is Z plane. Okay. And so here I have, let's assume I have an electric field E1, and here I have another electric field E2. They are not necessarily have the same angle. Okay, and the question is, what will be at this here at the surface? What will be the component at this surface? Okay. Now let's assume I have E2, the electric field E2 is equal to the component of electric field E2 is equal to 2x minus 3y plus 3z. Okay, and let's assume that epsilon 1 is equal to 2 times the permittivity of free space, and epsilon 2 is equal to 4 times epsilon 0. Calculate the magnitude of E1. Sorry, not the magnitude, component of E1. Calculate the component of E1. Now, we know using boundary conditions. What are the boundary conditions? The boundary conditions in electrostatics, it's telling us that the tangential of electric field 1 is equal to the tangential of electric field 2. Okay. It is also telling us that epsilon 1, the tangential, the normal of epsilon of 1 minus the normal of 2 is equal to the surface charge density. Are you following? So I need to use this to get the component of E1, or yeah, of E1, yes, to get the component of E1. Now let's assume that in this case, let's assume for the moment that there is no surface charge density at the. So what are the normal and the tangential component in this specific case? Who can tell me what are the tangential component of the electric field? Remember, the tangential component according to the surface, to the plane, to the surface, or the surface plane that limit or separate the two medium.
The tangential components would be EX and EY.
Exactly.
And the normal would be EZ.
Yeah, exactly. Very good. Yeah. So the tangential component will be EX and EY. This means that the E1x will be equal to E2x, and E1y will be equal to E2y. Very good, right? And now the normal component is EZ. So this means that epsilon 1 E1z minus epsilon 2 E2z is equal to rho s, but rho s is equal to 0, because this is, it's given. This is given. In this problem, this is given. But we could have another value. We could have, for example, rho S is equal to 2 coulomb per cubic per meter squared surface density. But in this case, I did not give it. Okay, so this means that we are looking for what? We are looking for E1. So this means that E1Z will be equal to epsilon 2 over epsilon 1 E2Z. We know that epsilon 2 is what? Is 2 times epsilon 0 divided by 4 epsilon 0. And e to z, what is e to z? E to z is 3. So it's 3 because e to z is 3. Okay, this means that E1z will be equal to 1/2, so 3/2, 3/2, that's it, right? This is 1/2, so 3/2, yes. So then we can calculate easily now E1. So E1 is equal to E1x, which is also equal to E2x. This is 2. So it's 2x and minus 3y and plus this one, 3/2 z. This is the any question?
So I have a question.
Yes.
Can you scroll up a bit?
Yeah, yes.
The E1x equals E2x. Is this like given or what?
Well, this is from here. Okay.
Oh, okay.
So
I have another question.
yeah, so let me just answer because maybe it's not clear.
Sure.
The tangential components are equal, and the normal components are related by this, right? So what is the meaning of the tangential component? The tangential component, if you have a surface, if you have a medium, so those are two medium. Here in the top is medium, let's say medium 1, and here in the bottom below the space is medium 2. What do we mean by the tangential? The tangential is any component of the electric field that is parallel, or the projection along the plane. So in our example here, our plane is x and y. So this means at x and y, the E1x must be equal to E2x, and E1y is equal to E2y. Okay? And then the normal component was z axis. So this means that the normal here, epsilon 1 E1z minus epsilon 2 E2z is equal to, okay? This is what we mean. So you had another question?
Yeah, I just wanted to say, isn't E1Z supposed to be 6 since it's 4 over 2, not 2 over 4?
Okay, so maybe yes. Okay, maybe I did let me check. Okay. So E1 is equal E2 over epsilon 1, right? So what is E2? Yes, you are right. Exactly. Yes, you are right. Yes, here epsilon 2 is 4. This is 4 over 2. Okay, 4 over 2 is 2. So this will be 6. Yeah, thank you. Yeah. Any question? Okay, so now we might let's give it in a green color. What would happen in this example? What would happen if medium 2 now, okay, so not necessarily in this example, but in another example. Yes. What would, yes, sorry. Yes, we can apply in this. So what would happen if medium 2 was a conductor? So medium 2 is a conductor. Yes, so medium 2 conductor will be the tangential component will be equal 0, which means E2x must be equal to E2y is 0, which means E1x must be equal to E1y is equal to 0. What could be the following? Please follow this. For example, I can give you E1, the component is equal to A x plus B y plus, I don't know, 5 z. Okay, for example. And I will tell you, if E2 was a conductor, E2, no, medium 2 was a conductor, what will be the component A and B and C? No, C, there is no C. So it is clear from here that if E2 is a conductor, we know that E2 X must be equal to E2, so E1X. But we know that it's a conductor means it's equal to 0. And we know that E2Y must be equal to E1Y, but E2Y is 0 because a conductor, 0. So this means that E1 will be equal of X, 0. There is no component along X. There is no component along Y. So E1 will be only having a component along the Z-axis, which is a normal. Okay. Any question? This is in the case of a perfect conductor. Okay. Now, if we have two conductors, conductor 1 and conductor 2, but they are not perfect. Neither a perfect conductor nor a perfect dielectric. Okay, so here I still have E1, epsilon 1, and E2, epsilon 2. But because they are not a perfect conductor, not a perfect dielectric, they still have sigma 1 and sigma 2, which is the conductivity. Okay. So we still have, by the boundary conditions, we have the tangential of electric field 1 must be equal to the tangential of electric field 2. And we also have, please follow this because this is very important. And we know that epsilon 1 E1n normal minus epsilon 2 E2n is equal to the surface charge density. This is always valid. This is always valid. But in this case, we have conductor 1 and conductor 2. And we know that G1 is equal to sigma 1 E1. This is a relationship between the current density and the electric field and the conductivity. The same thing, J2 is equal to sigma 2 epsilon 2. So what does this mean? This means that if I take this one and I use this one, so I get the first tangential, which is sigma 1 tangential divided by sigma 1, J1 tangential must be equal to J2 tangential divided by sigma 2. This is the coming from this one and replacing here. Okay. This one, you mean, Omar?
Yeah.
This is the surface charge density. The surface charge density. This is the, you see, you have medium 1 here. Let's say, for example, here, I don't know, in this case, it's conductor. We can, let's say you have a poor copper, a poor aluminum, and in between the contact, so you have a charge. And this charge has a density that is called ROS. Yeah, so it depends on the problem. Yes, it depends on the problem. I might give you, so no, let me just finish and I will answer your question, okay? I will finish and I will give you an example. So this is, as I mentioned, this is always valid. This is always a general case. But when we start doing conductor, perfect conductor, of course, E1t is equal to E2t is equal to 0. The conductor disappears, the electric field of the conductor disappears. In this case, we don't have perfect conductor, we don't have perfect insulator. So this means that we have a conductivity, we have current density, etc. So we will apply this here, okay? And now we can also take the second equation and do the same thing. What is epsilon 1? Epsilon 1, what is E1n? E1n is just the current density divided by sigma 1 minus epsilon 2, the current density divided by sigma 2. This is equal to surface charge density. But because we have a current, we have conductors, those are conductors. The current density here, in this case, must be equal to the current density here. Because the problem, if the current density changes, this means we are not in electrostatic condition. This means that the current and the density is changing as a function of time, which is not the case here. Because we start from the fact that this is an electrostatic condition. There is no change of the current or the surface, the charge, the current density as a function of time. We will see it in chapter 6 when they change. But in this case, because of electrostatic condition, conditions, J1n must be equal to G2. This is electrostatic condition. Otherwise, we will not have conservation of energy because electrostatic condition. So this means that J1n will be equal to epsilon 1 over sigma 1 minus epsilon 2 over sigma 2. This will be equal to ρs. Okay. Now to come back to your question, Noor, for example, I can give you something like I have two medium. Let's say this is sigma 1, this is E1, sigma 2, E2. Well, I can give you the values for E1 and E2, okay, and I will give you sigma 1, sigma 2, and ask you, okay, using the boundary condition, calculate the component of J1n or something, or the surface charge density and something like that. Yeah, all what you have to do is to use these formulas. So yeah, if it is needed, I will give you the current density, but sometimes I will give you, you will be asked to calculate the current density. Yes, the conductivity will be given, of course. If I give you a metal or a conductor, yes, the conductivity will be given. Okay. Okay, so this is as I mentioned to you, just exercise. There are some good examples in the textbook. But this concept, you should understand this concept. As I mentioned, I want to repeat it again. We always start from this. This is a valid boundary conditions for everything. And then we will see. For example, sometimes I might give you, I have two poor conductors here, conductor number 1 and conductor number 2. But I might tell you, like I gave in the example, for simplicity, there is no surface charge density here. Okay, for example, if there is no surface charge density, of course, J1n will be equal to 0. Okay, because if you have 0 here, this is not equal. Okay, or I can tell you, well, J1n is not 0, but calculate the conductivity of one of them. So epsilon 1n over sigma 1 must be equal to epsilon 2 over sigma 2 to overcome this surface charge density that is equal to 0. So this could be the equation, for example. Okay. Because if it is a poor conductor, J1n will not be equal to 0. Okay. So this means that this condition must be satisfied. I would give you epsilon 1, epsilon 2, sigma 2, and I will ask you calculate sigma 1, for example. Okay. Okay, so now I am done with this part because I wanted to explain it. Unless you have questions, let me go to, I'm just checking if I did not forget anything. Okay, now let's go to the same thing, but not the same thing, but chapter 4. Yeah, so another does perfect dielectric have a similar conduction? No. The perfect dielectric, no. Perfect dielectric, there is no, if you have a dielectric here and dielectric 1 and dielectric 2, of course, the only thing that we can do is the tangential of electric field 1 is equal to the tangential of electric field 2. Right? Because the reason we said E1t is equal to 0 is because it was a conductor. But in this case, no, it was not a conductor. Okay, so yes, it's a general case. Okay, but those are very good questions. Yes. Let's also, so yes, now I will go to another topic. Let's say that I am giving you the electric flux density of, let's say, a surface, a sphere. I have a sphere, and this sphere has radius A, okay? And this sphere has a electric flux density. By the way, this is a sphere, this is a dielectric sphere, the dielectric sphere, and the surface flux density is equal to rho 0, R, and R. Yeah. Now, please remember, when I gave you R, the unit vector R, theta, phi, which coordinate we are talking about?
Spherical.
Exactly, so spherical coordinate. So the question here is calculate the total charge inside the sphere. Total charge, the whole charge here inside the sphere. Okay. So what is the total charge? Total charge is, we use the Gauss law. Gauss law tells us that the total charge is equal, please pay attention here, is equal to the surface integral of the electric flux density times ds. Okay. Remember, in physics 2, we did the following: E ds, the Gauss law, is equal to the total charge divided by epsilon, right? Yeah. Well, actually, this is because here, if you bring this here, it becomes d. So this is exactly the same. Okay. Now, we are talking about the surface. So we are talking about the surface. We are talking about this blue surface, okay, which means the radius is a. So we are talking about surface, which means we have to integrate a double integral. We integrate over theta from 0 to pi, and we integrate from 0 to 2 pi, which is ds, but ds is equal, which is dx dy is equal to r squared sine theta d theta d phi. Okay, so the total charge is equal to 0 pi, 0 to pi of d. What is d? D is rho 0 r. This is d. Okay, times this one, r squared sine theta d theta d phi. We know that theta goes from 0 to pi, and phi goes from 0 to 2 pi. And this is just when you integrate over the whole sphere. And of course,
Professor,
yeah,
shouldn't we also integrate with respect to R?
no, that's a very good question. We can, well, actually, the reason we are not integrating over R, well, we can integrate over R, but the reason we are not integrating over R, because we are integrating over a surface, not over a volume. So what is this surface? Is this one, the one that I put in blue here, right? So what we will do, and at this surface, there is a specific value for R. R is equal to A. So you integrate over a surface with a constant radius. Did you get it?
Yeah, I got it. Thank you.
Okay. If you had to integrate over a volume, yes, you have to take into account the evolution of the radius from 0 to r. But here, no. Here we are talking about a specific value of r, which is A, just the surface. So we just replace r by A. Yes, so the reason I integrated over 0 to pi and 0 to 2 pi, this is just spherical coordinate. When a spherical coordinate, when you get a spherical coordinate, you have to integrate theta from 0 to pi and phi from 0 to 2 pi. This is how you build a full sphere. Okay, so this will give you 0 to pi, of course, r cubed. I can get it out of the, and rho 0 also, which is a constant, r cubed, the sine theta and d theta, and then the integral from 0 to 2 pi d phi. Okay, obviously here you can easily check that it's equal to 2, because it gives you cosine, okay, cosine pi. So this will give you 2 rho 0 r cubed, and this will give you 2 pi times 2 pi. So it will give you 4 pi rho 0 and r is equal to a, so it's a cubed. This is the total charge. Okay. Yeah. So let's go to now. Remember here, the reason I'm r is cubed because we have r that comes from the definition. This is given. I gave you the flux density is equal to rho 0 r times the unit vector. So there is one r here, and the other r squared is coming from the integral, the conversion from Cartesian coordinate to a spherical coordinate. So that's why it gives you r here and r squared here. So it gives you r cubed. Okay. Okay. So now just make the difference, or notice the difference that here I am talking about the total charge inside the sphere, and I use the flux, the Gauss law, right? Now I can also give another example, but now the volume charge density. Another example, I will give you D, and it is equal to 2x plus 3x plus 3x minus 2y, y. And the question here is calculate the volume charge density, and the second is the total charge. Can you hear me? Can you hear me? Can you still follow? Okay. Okay, so now the same thing at the end, I want to take the total charge. In the previous example, we used the Gauss law. Here, how can I get rho v? Yeah, one thing I did not
by finding the gradient of D.
Exactly. So please always go and look at the formulas. For example, this one. Yeah. What is it? Yeah, this one here. Okay. So now, an advice that I would give you is you have now this formula. When you start exercising yourself, preparing for the exam, try to get familiar with the list of formulas. So you don't have to spend 5 minutes every time in the exam, every time you want to look for the formula. Okay, so you can see that the first part is the Cartesian spherical cylindrical coordinate. The second part is about Maxwell's equations for electrostatics, and the third part for the continuity boundary conditions, and the fourth part for the magnetism or magnetostatic. Okay, otherwise you will just start wasting your time. So here, yes, correct, Shad, I think Shad who answered. So the divergence of vector D is equal to the charge, the volume charge density. Okay, so I will answer your question, Noor. Just yeah, yes, yes. Just that's a good question. Let me solve this one. So by the way, I'm not asking you questions because I want to go fast to do as much as possible. Otherwise, if you were in class, I would have asked you, okay, what do you think? How do you solve this? But since this is a review session, I would just solve the problems. Otherwise, you will be here for hours. So this is the component along the derivative, the partial derivative of the components along this plus the partial derivative. And you can easily see that this is the derivative here is 2, derivative here is -2, and this is 0, so this is equal to 0. Okay, so the partial is 0. Now, how can we calculate the total charge?
The integral of PV dV.
Yeah, so you integrate, you have the volume charge density, and you just integrate, sorry, dV, okay? But since 0, the charge inside is 0, it will be 0. Otherwise, you could also have done the same question. Yeah. Let me go back to this equation. In fact, yeah, so Noor was asking about the about why not using the volume integrating over the volume. Okay, integrating over the volume. Who can answer? So let me just explain something. So what is here? We have the integral. I want to add a new page. Here you have the integral over a surface ds. This is equal to the total charge, right? Now, if I go to the formula, yeah, yeah, yes, yeah. So what do you want? I just want to, yeah. So according to Noor, we can integrate over the volume. But if you want to integrate over the volume, you need to calculate the volume charge density, because the volume charge density will give you the volume, right? Right, Noor? And the volume charge density is equal to this. So you could do the following. You could do nabla d dv, and then you integrate over the volume, right? But then it will be a very, very lengthy calculation, because then you have to calculate this and then integrate a triple integral, including r. Okay, so it should give you the same result. But this is very easy because we already give you d and the surface. So in this, if you want to go this route, you have to calculate first the volume charge density, because you cannot integrate without over the volume without having the volume charge density. But those are very good questions. Okay, another thing is let's also calculate the gradient, because this I think we did not do before. Probably I did in class. So let's take a scalar that is equal to r squared cosine square phi. Which coordinate we are talking about?
Spherical.
We are talking
cylindrical.
Cylindrical. Yeah. So we are talking about cylindrical. So when we talk, at least in the textbook, spherical, we talk about capital R, theta, and phi. Cylindrical, we talk about small r, theta, and z. So since we are talking here about, phi, yeah, and so those are cylindrical. So calculate the gradient. Now, what is the gradient? The gradient, because those are spherical, you have to go to the formula and use this one. Okay, so you need to use the this one. So we are talking about the gradient. Okay, so that's, please, because remember, if you want to do the divergence, if I ask you to calculate the divergence of a vector, it's something else. But here we are talking about the gradient. So let's go and calculate the gradient. So the gradient is equal to, it's n. So I call it n here. So it's the partial derivative with respect to r plus 1 over r. And the vector r, because it transformed to a vector, 1 over r, the partial derivative with respect to phi, plus the partial derivative with respect to z. So what is the partial derivative with respect to r? It's just 2r cosine square theta, and then r, plus 1 over r. What is the partial derivative with respect to pi, to here, to phi, sorry. So it will be r squared times minus 2 sine phi cosine phi. I think this you can easily do yourself. And there is no dependency on z, which is 0. So there is no dependency on z, so the derivative with respect to z is equal to 0. This will give you 2r cosine square theta along r. Here you get minus 2r sine phi cosine phi along the, okay. This is the, this is just to give you an idea of the, yeah. So then let's go to another problem. Yeah, so if you remember, we talked about a field, for example, an electric field is solenoidal if divergence is equal to 0 and the field is conservative if the cross product with nabla is equal to 0. So this is very, very important. So this, of course, we already did the divergence. We can also do easily the nabla cross A. For example, if I give you A is equal to AX, X plus AY, Y plus AZ, Z, well, you can easily do this, set equal to X, Y, Z, and then, yeah, this is nabla, so it should be the first, okay? And then this will be AX, AY, AZ. And then you do the calculation. Okay. Then the Laplacian. Let's give an example about the Laplacian. So calculate the Laplacian of this vector, of this scalar, which is 4x y squared z cubed. So we know that the Laplacian will be equal to second derivative of v with respect to x plus the second derivative of with respect to y plus the second derivative with respect to z. Okay, so we can, yeah, so we can easily see that. Yeah, so here it will be the second derivative with respect to, and then you can do the calculation. I think, yeah, I think it's very easy to do. So let's go to something else. The last thing I wanted to show, let me see if I have, yeah, I wanted to mention three things. This is, I think you can easily do yourself. The second derivative with respect to b, for example, here, with respect to x, it will be 0. The second derivative with respect to y, it will be 4x z cubed, and so on. Yes, for example, let's take, I have a vector that is equal to r exponential minus r along r. So obviously this is spherical coordinate. And the question is, check if the vector is solenoidal and or conservative. Okay. The reason I gave this example is just because it's in spherical. Of course, if in order to check if it is solenoidal, you have to do its divergence, and divergence is given by you can go also to the formula, the divergence of spherical. So the divergence of a spherical is this one. Okay. Right. Now, in this case, there is no component along theta and no component along phi, which is very easy in this case. It's not complicated. Yeah. So here, the only component that is available is along r, and we do this AR. AR is this, AR is the component along, or AR is the component along the r axis. So here you have r squared. The second, the derivative, partial derivative is 2r. Yeah, so it's r cubed, the r cubed exponential minus r. And if you do the derivative for this, it's 1 over r squared. The partial derivative will be 3r squared exponential minus r minus r cubed exponential minus r. And this will give you easily 3 exponential minus r minus r exponential minus r. And you can see it is not equal to 0, which means it is not solenoidal, sorry. And if you want to do the conservative, you have to do h. And again, you have to use the formula, and you will find that it is equal to 0. You can do it. You will find that it is equal to 0, which is conservative. Any question? the last two things I wanted to mention here is if I give you let's say if I give you this we did in class, let's say a copper cable, for example, and this copper cable has a radius A and a length L, for example, and I ask you to calculate I give you the conductivity, so that we know that the conductivity is equal to the volume charge density times the mobility of electrons. Okay, we know also that the current density equal to sigma times the electric field. For example, if I have an electric field applied to it, we also know that the electric field is equal to the potential difference divided by the length. For example, if I tell you I apply a potential difference here, delta V, so what will be the electric field? So you calculate the electric field. You calculate sigma, for example, and then you would calculate the current density. Okay, and then we also have sigma that is equal to the number of free electrons times the mobility of electrons times the electron charge. So this is the number of free electrons per cubic meters. This is the mobility of electrons, and this is the charge. This is just a 10 to the minus 19 coulomb, the charge of the electron. So you will get a problem like that. So this is the reason I insist on this is because it is very important for you as electrical engineers to know these kind of things, to know the difference between current density, current. I might also ask you about the resistance of this copper cable. We know that the resistance is equal to rho resistivity divided times the length divided by the area, and it is equal to L sigma by A squared, and so on. So the last thing is chapter 5, which will be a bonus question. As I mentioned, chapter 5, we have this equation, which is as I mentioned, the flux that is equal to 0, and this is given. So the nabla cross H is equal to J. We know that the magnitude the electric field, the magnetic field is equal to mu the density. This is the permeability. Okay, and the vector magnetic potential is called A, and it is related by this cross A. So for example, I might give you, okay, A is equal, I don't know, 2x x plus 3xy y, and I will ask you to calculate the magnitude, sorry, the B. Of course, B, you will just go so x, y, z, and then x, y, z, and then it will be 2x here, and 3xy, and 0. And then you do the calculation, and then you obtain B. Okay. And in addition to that, remember from this is equal to mu J, just because of this, this. Okay. So this is what I wanted to mention. So this is will be a bonus question like that. So I am done. Basically, the exam will not be. So it will be in this what we covered today. So the concept that we covered today. I will stop here. I will stop even recording. If you have a question, please ask. Any question? No, actually, I did not. No, it is strange. Actually, okay. I just I will stop sharing. For some reason it did not. Yeah.